Characterization results. Average particle sizes, densities, and conductivities of the samples were given in Table 1. The diffraction pattern of BNT indicated the crystalline nature, whereas CS showed the amorphous nature. The XRD pattern of pure BNT has sharp peaks around 2 theta equals 8 degrees, 18 degrees, 21 degrees, 26 degrees, and 28 degrees that are typical of BNT. The XRD pattern of BNT/CS composites has peaks with relatively lower intensities than that of BNT. This indicates that the amorphous structure of CS covers the crystalline structure of BNT, which confirms the more amorphous nature of the composites. According to the TGA curves of the samples in contrast to pure CS, the residual amounts of the composites increased with increasing BNT content as follows: 89% BNT greater than, 86% BNT/CS 1%, greater than, 81% BNT/CS 5%, greater than, 57% BNT/CS 25%, greater than, 30% CS. This tendency can be attributed to high thermal stability of the BNT component. These thermal stability results of BNT/CS composites are very suitable for potential and industrial applications as new ER materials. According to the SIM results, CS chains not only intercalated inside the interlayer spaces of BNT but also settled on the surface of BNT layers, flocculated. The flocculated formation of the composites could be due to the hydroxylated edge-edge interaction of the silicate layers between the silicate hydroxylated edge groups and the CS chains. Some physical properties of the samples. Electrorheological properties. The electric field viscosities of BNT/CS/SO suspensions increased with increasing electric field strength and reached to 470, 980, 550, and 515 pascals S under E equals 1 kV/ohm, respectively, Figure 1. BNT/SO ER fluid exhibited to enhance ER effect with applied electric field to improve the particle's polarization ability and a typical shear thinning non-Newtonian viscoelastic behavior. When U is applied to the ER suspension, the magnitude of the polarization forces between particles increased and the particles rapidly formed fibrillar structure perpendicular to the electrodes, which resulted in enhanced electric field-induced viscosity. Effect of electric field strength on viscosity, K1, BNT/CS 1%, K5, BNT/CS 5%, and K25, BNT/CS 25%, T equals 25 degrees Celsius, C equals 25 weight%, and gamma equals 0.2 S-1. For the composites, the highest electric field viscosity, 980 pascals S, was obtained for BNT/CS 1%/SO suspension under E equals 1 kV/ohm, whereas the lowest electric field viscosity, 515 pascals S, was obtained for BNT/CS 25%/SO suspension under the same field strength. This result may be attributed to a decrease in the mutual action between the particles due to increasing particle size or BNT content, which reduces the possibility of the formation of strong chains between the upper and lower electrodes. Shear stress is one of the critical design parameters in ER phenomenon. The change of electric field-induced shear stress, tau E, of the suspensions increased with the increasing electric field strength as follows: 190 pascals BNT/CS 1%, greater than, 118 pascals BNT/CS 5%, greater than, 95 pascals BNT/CS 25%, greater than, 88 pascals BNT under E equals 1 kV/ohm. Change in G and G with frequency, K1, BNT/CS 1%, K5, BNT/CS 5%, and K25, BNT/CS 25%, C equals 25 weight%, T equals 25 degrees Celsius, tau equals 10 pascals, onde equals 1 kV/ohm. The external frequency is an essential factor for characterizing the dynamic viscoelastic properties of ER fluids. Storage modulus, G, and loss modulus, G, values of CS/SO, BNT/SO and BNT/CS/SO suspensions slightly increased with increasing frequency, Figure 2. These variations in G and G correspond to energy change occurring during dynamic shear process and are strongly dependent on the interactions between CS chains and B&T layer interfaces in the suspension. The G values of the prepared suspensions are higher than G values. According to this result, strong interactions were developed between CS and B&T interfaces, which enhance the elastic properties of these composites. In conclusion, characterization results confirm the introduction of the CS side chains into the B&T layers. ER activities of the suspensions increased with increasing electric field strength, dispersing particle concentration, and decreasing shear rate. Viscoelastic properties of the suspensions enhanced due to the interactions between B&T and CS. B&T-based ER fluids with improved ER and viscoelastic behaviors could be a good candidate as a smart material for ER applications.